right, everyone. Welcome to another edition of Pi Data Trinidad and Tobago. It is our 38th meetup. Today we have Mr. Kevin Sigobin, and he is going to talk about towards, hold on one second, towards using on-premise LLMs to control robots. So let's first go over the PyData Code of Conduct, and then we'll introduce our speaker, and then our speaker will get started. So, be kind to others. Do not insult or put down others. Behave professionally. Remember that harassment and sexist, racist, or exclusionary jokes and language are not appropriate for PyData. All communication should be appropriate for a professional audience, including people of many different backgrounds. Sexual language and imagery is not appropriate. PyData is dedicated to providing a harassment-free event experience for everyone, regardless of gender, sexual orientation, gender identity, and expression, disability, appearance, body size, race, or religion. We will not tolerate harassment of participants in any form. Thank you for making this a welcoming, friendly community for all. So with that, I'm going to introduce Mr. Kevin Sigobin. Now, Kevin is an electrical engineer and computer engineer who graduated from the University of West Indies last year. Over the past year and a half, he has been developing agentized AI systems for edge robotics. His recent work includes integrating AI with aerial drones, underwater ROVs, and most recently, a fully local quadruped robot powered by a large language model running offline using Jetson hardware, which I think we're going to be talking about today. His current focus is enabling real-time natural language control of robots using LLMs without relying on cloud infrastructure. Kevin's broader aspiration is to apply this work towards the development of AI-enabled prosthetics, creating assistive devices that are intuitive, intelligent, and responsive to human intent. So with that, Kevin, take it away, and we look forward to hearing your talk.
Hello, thank you for the wonderful introduction. Hearing a bit of an echo. Okay, I think it's going now. Yes, hello again. As Torian so wonderfully introduced me, I'm Kevin Sigobin, and I'm going to be talking about my journey towards using on-premise LLMs to control robots tonight. Well, let's get started. So, a little bit about me, why this is relevant to me. As Torian might have mentioned, well, not directly, but I'm from Trinidad and Tobago. I've been working on agentic AI systems for a little bit now. This actually is the biggest project to date. I've had so much fun with it, and I really look forward to sharing it with you guys. When I spoke about my aspirations to graduate studies in prosthetics, you might wonder, okay, what does this have to do with this? But this is a very large push towards agentic AI systems and localized LLM models for all robotics, because how are you going to put prosthetics that are AI enabled on people and have them need to be connected to the internet? It's not very good, I guess. So, as I spoke about my motivations to doing this, how does it affect you guys? This is the primer on levels of robot control. Here, I'll kind of explain why it's important to do. It's because robots have become so widespread in civilian and industrial settings. And they're actually quite difficult to control. This kind of shows how they have moved from extremely difficult to control to very little problems for users to control. I kind of started off myself with the manual control, thinking web interfaces for the robot dog, which I'll show later on. You then see things like shared controller systems with robotic cameras and stabilizers, where we're at now with task level autonomy, like fetch and deliver robots in warehouses. And we were kind of aspiring to go with oriented on autonomy, household robots like you would see in the Jetson. Jetson's telling them, hey, clean my kitchen, I don't go perform the task. These are all about giving vague instructions that anyone can give and being able to take that task and do it for you. It might sound scary when you think of dangerous applications like in the military, for example, but I think it's going to be more positive when you think of its application for healthcare. Being able to take care of your grandparents, your parents, the elderly, those who may not have a good grasp on these things, being able to take their medicines, be taken care of, to go to the washroom and cleaning up the house. That aspect of it has really come to touch with my love of the topic in the past couple of months. So let's move on to what are these LLMs and how does it help the core of levels of control? Well, you can't have an easier way to control the robot than speaking to it. How we us humans do have a conversation with these machines by talking to it. Well, the foreseeable future at least, agentic AI helps break these program intensive functions into very simple jobs where one agent might have a job to make a plan, another one might have a job to execute a plan. This is a high level way to view how an LLM can control robots, where you give the robot a command, the LLM planning agent turns that command into a broken down list of steps. The executing agent takes that list of steps and execute each function for the robot to perform. But LLMs are very large and very intense black boxes, so they take up a lot of data, and there are really two main ways you can look at using them: online or offline. Online has the benefits you would associate with it that you might initially want to gravitate towards. It's very low cost for prototyping, very low cost for the initial phases. It's in, instantaneously elastic, meaning that it's very easy to upgrade. It's managed by someone else, and uptime is managed by these large companies. But overall, these are all good things. The real things you want to look at are the benefits of mind control. It's low latency, requires no internet for the use of healthcare in these critical situations. The security aspect, which enables full control, which is a big part of how we ended up getting into this as well. Looking at how do we take this robot dog and build a web interface that circumnavigates the whole going online and using the dog's app on their phone. This also gives us full control for the customization, as I'll show you in that web interface coming up. Compute capabilities, allocations of the hubs. I'm having a bit of an echo, Tori. Yes, thank you. Compute capabilities and locations on the robots. When you see these robots have to use these LLMs, they'll need these GPU devices in order to function. Here's a range of, we can see the lower end of high complexity compute requirement. Here on the lower end, we see the embedded things on robots, the Jetson Nano, the AGX. You find them on drones and the small dog as I've been looking on. Most people here, I'm sure, will get at the laptop level, playing games on their desktop. You might also see that on much larger autonomous vehicles like golf carts and things like that. I've actually had the pleasure to move up from this level to like one on with Thinking, which was very old, but it was still cool to have. Finally, we see things like the GPU in OpenAI and these large corporations. what I'm trying to do basically show you guys is that how can we take something from operating on OpenAI and how can we operate it on this very small embedded devices? Some of the different devices that go from the Jetson family, from the Jetson family to the Jetson HF4. For the specific tabs, I looked at the Jetson Orionana and the Jetson HX performance. You can see here the relative AI power in POPs, which is tera operations per second for all you guys. That's 10 to the power of 12. The approximate cost, which as you can see what I'm talking about, very high front end cost compare, say $595, $249 to maybe like $20 to buy a bunch of credits from OpenAI. But the use cases are going to increase to potentially be utilized by a use case on robotics doing simple agentized tasks. So now we get to the dog I'm using. You might have heard of it. It's the Unitary Go-To, a really cool dog, really cool for doing tricks until we implement the LLM control. I found it as more a toy without the LLM control, doing tricks like crouching down, standing up, put it in AI mode to increase its balance, and I can do a handstand. Extremely cool for parties and events. Here we see some more aspects of the dog. It has a LiDAR, a camera, and a light, and a bunch of these functions, which made a good playground to start testing how we can control the functionality of the dog. How I started from this point was making, as I mentioned before, the web interface. The web interface circumnavigated the app and joystick and gave me an offline way to connect to the dog and run the functions and commands. As you can see, as I mentioned with the manual control, there are some issues. I'm not professional at how I implemented the functions, but there are issues with it. Like there are lock conditions that I have to account for, and having an LLM control with this will make things a lot easier. So we move forward to trying to use agentized LLM control, and we stumble across dimensional OS. What is dimensional OS? Dimensional OS is an open source framework for building definitive generalist robots. Where they start and where I help them is with their most Unitary Go-To integration. We've allowed them to create off-the-shelf agents to call the Unitary ROS2 nodes and WebRTC action primitives. In that previous video, I was using the WebRTC action primitive in order to do the function calling. Unitary Go-2 will allow me to do that same thing while connected to the LLMs. And we see a bit of a diagram showing how it operates, where you'd have a web interface on your x86 machine that receives queries from a user. Those queries are given to an LLM planner, which makes a request by providing the context window of the instructions to make a plan and all the list of skills that the dog may have to OpenAI's GPT-4. The LLM model would return a list of the skills that must be performed in order to complete the task. This is then provided to the LLM executor agent. This agent takes that and tells the model now, okay, now that you've broken down the steps, now execute these functions for me. And it's submitted, once the functions are returned, it's submitted to the ROS command queue. Hello? It's submitted to the ROS command queue. ROS command queue, where it will incrementally clear the queue and send these instructions to the dog and remove each one as the dog performs the task. What I did with what they had, this came in two phases. The first one, where I simply still use the OpenAI backend for model hosting, but put it on a Jetson or a Nano. Secondly, I tried to put it fully local. There are a couple of improvements I made with the first iteration. As I said, I put it on a Jetson or a Nano, a much smaller device. I implemented ASR, automatic speech recognition, with a Riva, which allowed me to control the dog not only from speech, but with the web interface. And they encountered the same issue with the locking up of the dog. From what I did working on my initial web interface, I was able to put a function to the command queue that when it has that lockup scenario, I cleared it by adding an additional command to put it in a correct state in order to perform the next command. After that, seeing that, okay, I got the OpenAI stuff working on the Jetson or Nano, I moved on to trying to do things with Jetson HDX, completely removing the whole system from OpenAI and the internet. So here's kind of like a result of when I did my first change. After the first change, what we're testing here are simple gestures, seeing if the dog can receive simple voice commands and perform them. Simple meaning have commands that directly reflect those functions of the dog. How we're doing these tests is, as I said, through Riva, it's going to, the demonstrator is going to say an activation word. He will say the command, simple name of the command. This functions just like the robots we have now. And it'll perform the task. This is what occurred. As you see, he said the activation rate can. He said it weird, but he kind of explained that as well. You will see here that the message is passed to the planner agent, which makes a plan, submits it to the executor agent, and the executor makes the dog stand up. Here you'll notice something very interesting when he moves on to the next simple command. When he says can stand down, it goes through the planner agent, but takes a second before it executes. That's because of my additional step to switch to the correct state to allow it to stand out. Moving on to the next test, we move on to a more complex test. Here we want to see if the dog is able to perform a series of tasks. Once again, just a list of the simple gestures directly correlating to the functions of the dog. Here we use the web interface though, because the Riva does have a bit of difficulty understanding the demonstrator's accent. So you'll see here, we'll use the web interface, give the dog a list of commands to do, the dog is expected to perform those commands in the order given. And here's what we got. First, to prepare for the test, he tells the dog to just stand down, and then he gives it the command to stand up and wave hello. You'll see the planner breaks that up into standing up and saying hello, and then the executor will then proceed to stand up and wave hello. This is where things get more in line with where we want to go with general, where we want to go with the task execution. Here we have a test where it's given a somewhat vague instruction to move forward, turn around, and return to its original position. We expect the dog to break that up into set steps. It'll make a plan to move forward 1 meter, 180 degrees, and then move forward again 1 meter. The executor is supposed to take that and give Ross the correct parameters in order to express those actions. And here's what we see. The demonstrator types the query in, move forward 1 meter, turn around, and then return to the original spot. And then the planner will take that and break it up into its set of steps. You see here that the planner does that correctly. It's able to take that somewhat vague instruction and say, move forward 1 meter, turn 180 degrees, move forward 1 meter, and spin 180 degrees again. But this is not what we see when the dog tries to execute it. Oh, let's start with you see the dog move forward 1 meter, we hope. It turns not 180 degrees, and then it just kind of stays there. So what happened? Well, the executor was due to a problem potentially with the system prompt or how the functions are coded, was unable to give the function the correct parameters needed to execute the task properly. And thus it tried to perform the action, but failed. So we can see that we're not exactly where we need to be with this. But regardless, I still try to take it a step further. I tried to put this on an entirely local system. And I took the OpenAI backend for the executor agent and created my own for the local Jetson. I changed the client endpoint to call from the AGX organ that I showed previously to get the LLM responses. I switched the OpenAI tokenizer to a Hugging Face one, more general to the different LLM models I use. The model name was explicitly GPT-404, and I changed that to the ones I was testing early on in my phases, Llamas 3.1 and Quen. Streaming responses change from being a response model, which was very efficient in forcing OpenAI to give a response format with a specific structure. This was not possible with other models, since this is something specific to OpenAI, but attempts were made to fix that, as you'll see in the planning agent. And then the send query method functions basically the same, except for the local Jetson version. To kind of account for the change in response model, I lowered the temperature to allow less variance and try to force it to follow the specific system prompt I provided with the specific examples. The planning agent pulled directly from the execution agent simply provides the execution agent with the required parameters. As you see here, you see the same changes that had to be made, except more specific to be passed to the executor. The LLM model I used was pulled from NVIDIA Jetson AI Lab. On the AJ forum, I use models from Jetson AI Lab to run and then query that Docker container. The backends I used was Pseudonym and Olama. Pseudonym was really good at planning the task, but it was not able to execute tasks properly because it was not OpenAI compatible. Olama, however, was OpenAI compatible and did well in executing tasks, but could not plan things well. I'm here to note from my journey with local LLM control. For the unit test of getting the planner to work and the executor to work, I was able to get them to work independently, but as soon as I tried to use one model to control both things, that's where things kind of fell apart. What do I plan on doing in the future? Well, I implementing fully local control. I have some ideas of how to do this. One is that I can find an LLM with the proper backend that can perform the planner and executor tasks. Another option is to try out using Triton Server, since I am on NVIDIA Jetson, to better use multiple models. So I don't need to find one thing to use. Based on the task given, it can pull from different models. And then number 3 is to optimize. Number 3 is optimization to make this more functional on a Jetson or an app. As you saw, it's running on a Jetson or an app, and then pulls an ATX. I would hope to change it in the future. That initial simple task could run on smaller models on the Jetson or an app. If it takes too long or it fails to execute the task, it then pulls larger models running on the Jetson ATX or an. And then if that fails, then it could pull OpenAI's ChatGPT-4. Well, that was my presentation. Thanks for listening. And I showing you a bit of the dog walking around and dancing entirely on its own at the AI conference I attended a little while ago. This is held together with Velcro, but it did very well in my strength test. Yes, I get a bit nervous on camera, but thanks again for listening, and I hope you'll take the opportunity to see what you guys can do yourself, because again, all this is open source, all this is very much accomplishable by anyone of you. Thanks for listening.